So I'm relatively new here, so maybe some of you just have no clue who I am. That's fair. I don't really know either. Still in the process of figuring that out. I think that's like a journey kind of thing for most people, anyways. But I'm not a neuroscientist, right? So I'm a machine learning engineer, and I worked with EEG data more as like from the machine learning prediction side. And the idea is really we could maybe find a really nice biomarker and then see if we can launch this into a startup. But we really need another round of data collection and much more. And so for that, there would be more funding necessary. And yeah, I'm not an EEG specialist, and so I don't really know how to do the collection for that either. I don't know how to do the proper cleanup for that. So there's a lot of things that you guys all probably know that I don't know, and there's going to be probably things that I know that are completely new for you. So I'm not sure how much of that will be. I'm not sure how much of that will be the focus of today. I tried to make it very accessible for today, so it should be really easy to get into, and it's going to be more on. Mostly going to be on one paper that really motivated me towards like really good scientific rigor in the work that I was doing, and so I'll be mostly presenting as if I was talking about the paper from that one. So I think it's been a few minutes. That means that we can get started. I'll display the chat really quickly. So this is the chat as it is now before we begin. And I've just introduced myself, and I'll be starting this short talk. I'm aiming towards an hour about EEG analysis, ERP analysis, mostly what not to do. And also at the end, we'll talk a bit about my work, which was in tinnitus. All right. So that was that. And so for today, we will be talking about two parts, as I said. First off is going to be really focused on this paper reading, which is about one specific thing that commonly goes wrong in EEG and ERP analysis. But if you've never really worked with EEG or don't really know what ERP even stands for, that's completely fine too. At any time, you can interrupt me. Just write your question in chat. I will try to respond. There is time for this, right? So if you guys don't talk at all, we will probably be through this in half an hour. So I'm going to hope for someone to interrupt me so that I can respond to that question. So it looks like I actually prepared something in advance. But yeah, if not, we'll be going very quickly through this introduction to EEG, and then really spend quite a bit of time, especially with the paper reading, which will quite naturally lead into like really the four horsemen of EEG analysis and research. And then I will finish that section up with talking about maybe what we can do, like as researchers or even as engineers, right? So also as engineers, you don't want to be presenting bogus results. And so I'll be spending some time there. Finally, I will also try to spend some time about my work, but I will have to say in advance, this has not yet been published. It's very close to publication, some of the papers, but it's not fully published yet, and so therefore I can't really reveal everything. It could be seen at some point. This talk could be seen by my colleagues. It's not a super big world, this EEG and tinnitus research. So if so, hi, it was super nice working with you, and I hope that we can get to publishing the paper quickly. All right. So without further ado, let's really quickly look at EEG, what we measure with EEG. As far as I understand it, maybe some of you already know quite a bit better, but let's look at what EEG is and what some of the limitations are, of course, as well. So it looks a bit like this. There's many different caps, but you'll have electrodes stuck on your scalp or on a cap on your scalp. And these electrodes, they will measure electrical signals. And these electrical signals really generate as a result of like action potential in the brain. There's no screen share. Oh, there's no screen share. I'm really, really sorry about that. So I was looking at my recording, and the recording was doing really well, actually. But I will just quickly share this. There we go. Thank you for pointing that out. That's a rookie mistake. Rookie mistake number 1. All right. So now there is a vision, right? Or no, still not. Okay, perfect. Thank you so much for pointing that out. I was just talking blindly and you were just listening calmly. Yeah, that's good. Okay, all right. So I will just presume that y'all were captivated by my story and didn't need slides, which is good because the slides were not really anything special to begin with. At some point, I got really bored from my own slide, and so I inserted some jokes. I hope that is appreciated at that point. But yeah, we just quickly go through it again. Thank you very much for your patience there as well. And so this is really what EEG can look like. This is just one example. And what you get out is something like this signal, right? So you will have one signal per electrode, and it's sampled very rapidly. So in our case, we were sampling at, if I remember correctly, 2048 times per second, right? So this is a lot of data coming in every second, and it's multivariate, right? So for example, maybe these are around 64 channels, maybe. And you get a lot of data there as well. And so essentially it's recording this electrical signal generated by the brain. It will also capture a lot of other noise, but I'll just ignore that for this moment. Those who have worked with EEG before or are familiar with it will know. And we also know that in this signal, certain things really stand out depending on what action or what action the participant is performing, or what especially what stimulus they are receiving, right? And so this can show up either immediately after the stimulus is presented, but we can also see it in how, for example, these frequencies, right? So we see that here it goes up and down and up and down, up and down. It might go up and down more rapidly. It might go up and down with a stronger amplitude. It might start becoming more in one frequency compared to another. So these are all things that physiologically we already know, or at least experts, not me, already know. And we use this to find out maybe other things, maybe to use it for diagnostics. It's very, very useful for that. So one way to do that is to look at the event-related potential. So in this case, we have, let's say, an event, right? So let's say a stimulus, and then we can measure really what the electrical signal looks like very shortly. So we are talking about a time span of like literally milliseconds after this stimulus was presented. And this is given as potential. Sometimes it's listed with the negative potential up and the positive potential downward. Sometimes it's the other way around. I would not be able to tell you why this is. Maybe someone in chat knows, but I have no idea. Either way, just pay attention to the sign there if you're really interested. Otherwise, it's good enough to know that this can show up and down. What also is really interesting is that this signal is super noisy. So usually we obtain a much clearer picture only after averaging data across many repetitions, and sometimes also across multiple patients or within one patient. It depends a bit on the experiment setup. All right. So this is one way of analyzing the EEG waves that you get out. Another way to look at it is to look at like the frequency component. So sorry for blasting your nice calm black screen with a white graph, but this is just one example that I found online of what that could look like. Here you have like a spectrogram is what it looks like, and it maps out the frequency over time. And you could see, for example, that here at the S7 segment of the experiment, really at the lower frequencies between 10 and 20 hertz, there is really something happening here. And this might be found by just looking at maybe averaging only one type of trials, or maybe by looking at the contrast between two different types of trials, right? So very often we are interested in how one type of trial differs from another type of trial. One thing that I skipped past, but that I also want to mention is that we already know quite a few ERPs in the we already know quite a few ERPs from the literature, but before I get into that, I see there's like a small question. I didn't know that electrical signals, you could get that from the exterior also. Yes, and what is the strength? It's very weak, and it's what the scale is in individual microvolts, I think, up to like tens, at most 100 microvolts, but I think it's normally below that. So it's like super weak, and there's actually quite a lot involved work in getting it parsed out from background, getting it separated from all the electrical signals that are generated when you move your muscles and those kind of things. So yeah, it's actually a really complicated field of study, but it's one that I did not go all too in depth in actually. Yeah, it's also one thing that I should note is that this is a really good point, is that it's on the exterior, right? So you can do some source localization by seeing if, let's say, a signal generated quite deep in this area, then this signal should also show up across multiple electrodes, along with a lot of other signals also. And so using advanced signal processing methods, researchers are able to pinpoint down the source of a action, not an action potential, but of the electrical signal quite well, I would say. But it depends often on a lot of repetitions. However, typically when you don't have this many repetitions, the resolution spatially is quite poor, right? So you only have 64 electrodes, and they measure something they measure a lot of the surrounding signals. So spatially, the signal from an EEG recording is typically quite poor, but in terms of the temporal dimension, in terms of time, it's actually a really high resolution, right? So like I said, it's sampling, it can sample 1,000 to more than 2,000 times a second. So this is really interesting, and it contrasts with something that is spatially quite rich, like fMRI, but that is temporally poorer. But fMRI measures something else, of course. Yep. So I hope that answers the question a little bit, and also explains a little bit of the challenges with EEG and brain imaging in general, right? So this is much less invasive than other methods can be, but at the same time, you get a much more complicated signal out. Yeah, so some ERPs that we know, P1, which is typically referencing whether it's positive going or negative going, and the 1 means 100 milliseconds. Yeah, so that's exactly right. I think that's pretty correct. The N1, negative going at around 100 milliseconds. The time window, it really varies a bit depending on the task, and you'll really have to look at the literature whether there are known components for your specific task. But yeah, these are just some that are known. Some of them are listed. If you're familiar with, for example, the Stroop task, then this really elicits the negative going amplitude at 200 milliseconds. And very often for these specific tasks, we also know the electrode location, which is ideal for measuring this. P3, the P300, is also really famous for being the oddball paradigm. And there are more, of course, right? So you can also say like, oh, there is like an N4 component, or like late positive potential, which can be like 1 entire second still after the stimulus presentation. And so they're all associated with different things in the literature. But it's good that these things are known, of course, because then we can relate our work to existing literature, of course. Yeah. So I showed a little bit about what the frequency components can look like. You can also map them out over the different electrodes, and so you can get like a very nice highlight of where the cortical areas with significant diff or with a large power difference are. But these are just tools or visualization tools for the scientific communication and also for the scientists to look at. Okay, so now that everyone is just as much as of an EEG expert as I am, we can start looking at this paper, which really inspired me to really do more scientific rigor in my work, right? Because as it turns out, you can get statistically significant effects in literally any ERP experiment, but there's a good reason why you shouldn't. And this is also the title of the paper by Luck and Gaspellin, which I think, if I remember correctly, were at the time of writing this professor and postdoc at the University of California, if I'm correct. Might be messing that one up, but yeah. So this is really this one paper, and it presents it very similar to how I'll be presenting this, and I'm presenting it in this manner because this is really how it impacted me. Okay, so they took data from a prior experiment, but the long and short of it is that they did an experiment with participants where the participants were given this EEG cap, and then they were shown digits or letters, one after the other. Let's say there were mostly letters, right? So let's say 80% letters and 20% were digits. This is due to another experiment, but they took data from there. And then the participants were asked with saying whether they saw a letter or whether they saw a digit, right? And so, like, let's say the digit, you press with your left hand, and when you see a letter, you press with your right hand. But unbeknownst to the participant, they snuck in some repetition, which was to the participant, to their knowledge, completely irrelevant, right? So, for example, this could be a sequence. So maybe first the participant saw a B, then the participant saw a G. They pressed correctly again. Oh, okay. So they press right. I see here in my own figure, they say that they press right for digits. Oopsie, but you get the gist of it. So they press left. They saw a letter again. It's another G. Whatever, doesn't really matter. They press left again. And so for this work of research, let's say we are interested in finding out if we can see already from the ERP response whether the participant is already aware of this repetition, right? So even if it's irrelevant to them, they might still be able to respond faster to being presented the same letter. And they might maybe respond more accurately when the same letter is represented twice. And we are interested, maybe neurophysiologically, where this happens, when this happens, right? Like, does it happen early on at already 100 milliseconds? Does it happen late at like 400 milliseconds? So this is, let's say, something that we want to answer with this study. Okay. So we did the study, and we can now look at grand averages. Of course, we do very typical EEG recording and very typical EEG processing, like filtering, artifact rejection, all the stuff that I don't know how to do. And finally, we do some averaging. And in this case, it was quite rigorous, I would say, because they had 800 trials. So imagine sitting through 800 letters or digits. Oh my God. And of these, 640 were like letter trials, and 160 were digit trials, right? And so in the letter trials, in this specific research, we are mostly interested in the letter trials where there were repetitions. So these 128, which are the frequent repetitions, the dotted lines in this case, contrasted with the non-repetitions. Now, all these electrodes, they are given a name, right? So like FP1 is typically located on more towards the front of the scalp, and then C4 is more towards the top of the scalp, let's say. And so these all have a name, and they are recording their own signal. But after averaging, most of the noise evens out, and we actually see that after averaging, there is like at 100 milliseconds, there is like a P100 response, it seems. And there's maybe also some difference also in amplitude, but maybe even on onset. at like the 200 millisecond between the two trials. So that's really interesting. Let's see if we can find a backing in the literature, see if we can do some statistical analysis on this, so we can just do a t-test at the for the amplitude at this time point, for example. And yeah, so the research was done, and there was some backing in the literature. Of course, we could say like maybe like P1 really focused on visual attention, which could be already noticing the repetition, and P2 could be related to the categorization, and so really recognizing this letter because it showed up earlier. There's very fast, very strong categorization, and this could explain maybe a faster response if we saw something like this. So that was the research. Also, the t-test, they were significant. I think the P1 was at maybe 0.01 and the other one was at 0.02 or something like that. So at least at like an alpha at 0.05, this is significant, right? So very nice. This is super cool, but does anyone already see where maybe I'm going with this, or maybe there's like already a problem here? Does anyone have any ideas as to what could be going on, or is everyone like, no, this is actually like I've seen research like this before. This is thus far it's super normal. Like where are you guys at in terms of like a feeling?
I was wondering about this idea of the time frame here.
Yeah.
So I'm guessing they show the letter at 0 seconds, and then you measure the activity afterwards. I'm just double checking the scale.
That's
there.
right. That's right. Yeah.
Okay.
When we do visual, hi, this is Pan. When you do visual evoked potentials, typically you see a visual evoked potential in the occipital cortex at around 200-ish milliseconds.
Yeah.
So seeing something at about, this is about 100, this is pretty late.
Okay.
The second issue is that this is what, 4 microvolts is the scale. So this is what, 1 microvolt. That's tiny. Like the margin for error is enormous, I think.
Yeah, but they did like 800 trials per participant, right? So I mean,
I understand.
It's a super tiny effect, but I mean, they could pick this up, right?
I don't know if I believe it, but
okay, that's good. We'll keep this.
I'm happy to listen.
Yeah, no. I mean that's very fair. I think this is one thing that we'll run into later, and it's like, it's not. So I will give a little spoiler. It's not really this that you pointed out, but actually effect size is very important, and this is a very small effect size. Even for
amplitude.
Yeah, like as you said, like the amplitude we're talking about, like a difference of like a single microvolt, if that, which is very small. Which is what you pointed out, right? If I understood you correctly.
Yeah, more or less.
Yeah. Is it about accounting for noise and seeing which spikes are actual signals, and then correlating the presence of spikes with stimuli the test subject is interacting with? So this is very close, I think. This is very close, but it's not it. It's not it, but it's very close. Right, so there's a lot of noise there that we know, but we kind of average it out, let's say over 800 trials. Let's say 800 trials with their participant is enough to find this significant 1 microvolt effect, which I think is possible. Like it's definitely possible for sure. If it exists. Correlating the presence of spikes with stimuli, the test. Yeah, so this is typically not super important because we assume that we have to, at some point we have to assume that for the trials, for the few trials that they start to mind wandering, it averages out, and the very few trials in which they really were late in responding, we can categorize those as outliers. This is very typical pre-processing where you remove, where you really have to remove trials where you have strong reason to believe that the patient was not actually observing the stimulus at the same time. Because otherwise, as you correctly pointed out, Dan, there is no real alignment anymore between the onset of when the participant is actually seeing something, right? So, but you're somewhat close as to what's actually going on. Do we have further ideas, or am I going to spoil it? it's funny that it's not being picked up on, because I think we know papers that present their data like this, especially if you're into this material. This process, this thinking process, is not strange, and yet there is an inherent problem with this, and that it was presented in this manner. The paper also presents it in this manner, and that it's presented in this manner makes it very normative, I would say. But then when we get to the reveal later on, I'm waiting a little bit. Maybe I see someone typing. Maybe there is some other ideas or suggestions. But yeah, when we get to reveal, I think this really shows how cautious we need to be in EEG specifically, because EEG is a little bit different from maybe more behavioral studies, in that we have this super rich data set. We have a super rich we have many dimensions, like 64. It can be even 128 electrodes. We are measuring so often each time, right? So we could be looking at. We have so many different ways of analyzing it. We're looking at the ERP now, but we could be looking at different frequency bands. We're not even really taking the how should I say this? We're not even really taking the temporal dimension into account. We're almost treating it as different categories, right? So like the P100 is categorically different from the P200, but maybe actually what we're interested in is the way these things change over time. So yeah, there's like a lot we can do with EEG, but this makes it very powerful in a sense. Like I said, a good signal processing, you could even do source localization, but it makes it also very dangerous. You can get bogus result very easily. So time for the big reveal. The labels were randomized in this experiment. No effect should be observable. We fooled ourselves. There was nothing here. This is just purely random, right? If you've looked at these spurious correlations before, they are somewhat infamous, I would say. Like, you will know that something like the amount of movies released by Hollywood correlates with the number of heart attacks in a year or something like that. I'm not sure if that's correct, but that's the idea, right? But just because they correlate, if you find enough to correlate, eventually you will find something that is at any alpha level statistically significant. And so the reason that we found something significant at the P100 or the P200 is because we already did many implicit multiple comparisons, right? So we actually, looking at this, there are many more electrodes than just these listed here. As the researcher, we were looking at all these different electrodes, and then we were looking at maybe something that fits our narrative or our expectations, right? So we are expecting something around 100 milliseconds. We are expecting something around 200 milliseconds. And it fits. Maybe it even fits electrodes-wise, like location-wise. Maybe it even fits based on the literature. But still, these are randomized labels, so nothing should be observable. And this really stood out to me because it's such a normal workflow, right? So of course you're going to be looking at your data first before knowing what you can even test for. This is like a highly complex multivariate signal. You can't just throw around thousands of tests, right? So this blew my mind, and they really discuss how much of a problem this can be, not just in EEG, but also fMRI and other like really data-rich domains. Yeah, so actually whether something was non-repetition or repetition or not is just completely random. So it didn't actually relate to what we are showing here at all. Yeah, so for example, one trial will be counted as a repetition and one trial will be counted as a non-repetition normally. But for this setup, what they actually did is that afterwards they just shuffled it, right? So afterwards, if something was a non-repetition, maybe sometimes it got the label of repetition. If something was a repetition, maybe it got the label of non-repetition. So it was shuffled to still match these numbers. but there should be no positives that you can find in this, because we literally randomized the data, basically, at least the labels. So what does that mean, right? So it means that a lot of things can go wrong. I'll look at this in a little bit more detail and then also list some other things that can go wrong before continuing as to some of the suggestions that the authors give into how we can address this. And you'll find that there are other horse people of what can go wrong, and they are very related to each other, right? So they're usually all a form of like p-hacking and harking, like hypothesizing after results are known, and ignoring some form of the multiple comparisons, right? So in this case, the researcher was already implicitly in their own mind making different comparisons. So this is like really an example of selective analysis, or maybe like experimental degrees of freedom. So they can choose where to apply an analysis, and if they know that this is already like looking quite promising, then this will obviously bias your results to be more likely bogus. Other things that are common in EEG are things like confounding factors, right? So in EEG especially, there can be so many things going on, especially if there's a mismatch between what patients have to do in one trial from another one. So in this case, for example, one thing that patients have to do in one case, in one trial, is press with the left hand, and in another trial, they press with the right hand. And so are we really... It says green on my end. All right, so it should be fine. I'll just continue, and Wizzy, you'll have to look this part back then if you're still interested. Right, so selective reporting really means that it's refers to any form where we are attempting various tests, and so you can feel like, as an EEG researcher, you can feel like you're not doing selective reporting because we first did a t-test, but this didn't turn out interesting because this didn't turn out significant because we didn't we didn't take the temporal domain into consideration, and then we maybe fit a regression line which takes over time, which takes the temporal domain into consideration, and then we see, oh yeah, so here it is looking a little bit significant, and then we report that, right? So it's very easy to also get dragged into this, because sometimes this is also warranted, right? So if you see that from the data, you really obviously see that there is this temporal effect, you'd almost be stupid not to try to fit a model that takes this temporal dimension into account, right? That's how you feel at the moment. But then this obviously biases the results again, and so we need to address that. And finally, there's like also very common in EEG, I would say, it's like post hoc data processing, right? So maybe we don't see significant results because we didn't take eye movement artifacts into account. Okay, so we remove the eye movement artifacts. Okay, so maybe there are still some outliers from when patients got distracted, and so we can spot those. Okay, we remove those. Eventually, we remove enough until we find significant results, and then we report those. And this, of course, also really can bias your reporting towards finding bogus results, and your research towards finding bogus results. Okay, so some other, I would say, really variants on more of the same, right? So multiple comparisons is at the top. You can actually make multiple comparisons, and it can be really good to do that, but you'll have to adjust your P threshold for that. Selection bias, where maybe you're asking only students, right? So typically, like the weird acronym pops up here as well. This is also just applicable to broader research. I'm sorry if I'm repeating something that has already been hammered into you in like statistics classes, but I found this presented in a very inspirational way, and I think these are also quite related. So I'm just putting them here as well. Progressive data collection, where you're inviting new participants until you have managed to average out all the noise and finally find these significant effects, right? So, and there is much more. So what can we do, and how can we like really aim towards doing the best science possible? Well, what they mention is, of course, at the very top is like pre-registering study design. But this is not always easy because on the one hand, I said there is like P100 and N100, these ERP components, which are already known in the literature. But if you perform a slightly different task, very oftentimes, we don't really know when or which components should show up. So then what do we do if this time window for the component, or maybe the site for the component, isn't really known? You can do like something like a function localizer. You can register that in advance. You can say like, okay, so I will write something, I will use some algorithm which is able to spot these peaks for me. But maybe it doesn't really apply to your effect. Maybe you're doing something like more in the frequency domain. So maybe that's not a very obvious thing to do. Then there is like a collapsed localizer for ERP specifically. This is, I think, a really good approach. This is essentially where you're just averaging all of the data. Yeah, so I got a question asked that whether there will be slides available. Yes, the slides will be available, and this is also going to be recorded. And I got a question about the experiment before. So in what way was the data randomized? So this is not my work, right? So I'm presenting, I'm more doing like a paper reading in this part of the presentation. And so the data was randomized in that the recording was still unaffected, but we arbitrarily assigned them to be a repetition or a non-repetition. So when we contrast this after averaging for all repetitions and we're averaging for all non-repetitions, if we then average it, there should be no difference between the two, right? Because the two labels were assigned randomly. But we still were able to spot moments in time at like the P100 and the P200 where the signal did seem to be significantly different from the two different trials. But this is not really a true positive. This is, of course, a false positive. Does that really clear up the confusion there? Okay, and while we're waiting on an answer there, I will just continue a little bit with explaining the collapsed localizer. The collapsed localizer here is where you average your signal, but you don't average it on the two different conditions that you're interested in. No, you average it across everything. And then maybe you see, okay, so there is a strong P100 component. I don't know whether these should be different, but maybe from the literature, I'm expecting it to be different. And so then we see on the grand averages, we see a difference, and we take only that window for the t-test. We look at nothing else, and only afterwards we start looking at the per condition averages to look at the differences between the two different conditions. So this is one way that you can kind of have your cake and eat it too, right? So you, on the one hand, you don't have to pre-register literally everything beforehand, but at the same time, you can also be more robust. No, so that's a really good question. So it's not necessarily on all nodes. Typically, what I would recommend in order to find good electrodes is to average, let's say, locations, for example. So if you're looking at maybe mostly a certain cortex, you can average the few electrodes that cover those, or pick the ones that you are most interested in based on existing literature in advance, right? So this is really also part of the pre-registering. But you could also, in theory, you could also just average across all trials, but still look at each individual node, right? So there's not really a problem with this because you're not able to know in advance whether there's going to be a difference in one single node. You're just seeing that, oh, one of these 64 nodes or a couple, a local group of these 64 nodes really have a strong positive going amplitude or negative going amplitude at a specific time point. And only after you've decided on the location to look at, only then do you separate again the two different conditions or three different conditions or whatever, and look if you actually find a significant difference. Does that kind of explain how the collapsed localizer here works? How you can still look at the signal without biasing yourself? Yeah, so this how you group across nodes, electrodes, really depends a bit on the experimental design. But the idea really is that you don't separate out the data between the two different conditions ahead of time, right? So you decide on what to look at only by the total grand average, and then you separate out the two different conditions. Because if you separate out ahead of time, you are already looking at spots in the data that look significant to you, right? I mean, this is super tempting. Of course, as a researcher, you want to immediately see if your data is good, if you found something, right? But this is a trap in that sense. And you can also do other things like full testing. Like you can actually run this t-test on everything, but then you will have to be much more lenient in your p-threshold correction, right? So Bonferroni correction will no longer be applicable. You will need to do a little bit of different testing, different correction. But it's possible. You can also do permutation testing, and there are some other ways to account for it also. And lastly, but definitely not least, is if it can be replicated, that's of course also really the golden standard, right? Very often there will not be budget to run the exact same experiment twice, but if your work has some practical implications or theoretical implications, then there might be incentive to continue researching on this. And usually as part of the validation process, that research will try to replicate the previous research. So this way we can get away with building on top of data which may have false positives, because we are in the process quite often also expecting and replicating previous findings. Right, so the real solution to all of the ones before is always going to be it depends, but there's many ways to get around it, and specifically we used this collapsed localizer for the ERP study. So that's really nice. Oh, okay, so that was really the majority of today, and we'll also briefly look at how I applied these things and further EEG analysis for tinnitus, but I have less to present on this because I'm not able to really show everything quite yet. So I hope this was already quite interesting. I hope that even if you already knew a lot of this, you have like I did, a rekindled desire really to be rigorous in your work. Maybe it's easy for me to say this because I am not in the academic world anymore. I was also never employed as like a PhD or the like. I was more taken on externally as like a specialist or expert. So in that sense, I am much freer to say, oh yeah, this could be a false positive, right? For a lot of people who do research, the reality is that they are always not just excited and curious, which can really, like I explained before, it can already bias your approach, but you're also really incentivized to publish. And so you are incentivized not to show this or to hide these things. So if you had to apply many different tests, you're incentivized really to show only the significant one. And this is a problem not with any individual person, I would say, unless you're doing it really like intentionally and consistently. But most of all, this is a problem, I think, with the current incentive structure. So I want to also pull some attention to that. Yep. But let's have a look at tinnitus. What is tinnitus? Well, first of all, I want to say I don't actually like talking about tinnitus. It gets a bad rap, right? So it's like this noise or sound, phantom sound that someone hears that is not actually there. It has no known cure, though there are ways to reduce it in many people. And there are known ways to make it much less annoying or harmful, let's say. But also in many cases, it can be like super benign, right? So like 10% of all people are known to have tinnitus, so it's like a super high percentage. But for a lot of people, they don't have like tinnitus, distress-related symptoms, so they just experience it much like any other symptom that they can just, much like any other stimulus that they can just ignore, right? So like seeing your nose, feeling your clothes, and here you go. Now you do see your nose, and now you are blinking manually. There you go. You got that one for free. Hope you enjoy it. But yeah, I mean, on the downside, it is super common, right? So it's like it's weird in a sense that there is no cure. It's weird that there isn't even a biomarker. Where is the biomarker? Why is it so hard to really objectively measure someone's tinnitus? If there's so many people with tinnitus, why is the best metric that we have a subjective questionnaire? Do you hear this sound? That's the questionnaire. Well, it's not really the questionnaire. There's a bit more. But yeah, I mean that's absolutely true. That's absolutely true. So a comment is that if you think about it, you could say this what I said about tinnitus for a lot of different brain pathologies. As a clinical neurologist, I understand the love-hate relationship. Find a cause and it's bad or benign, and you get a patient that will be in its own way your personal tinnitus. Because the tag thing really won't go away. Yeah, exactly. Yeah, so I understand your perspective is a little bit different as a clinical neurologist, but I think we experience a little bit of the same hesitation and relationship here. So yeah, but so many people have this. I mean, there's not that many brain pathologies that are as widespread, I feel. If it's even a brain pathology, maybe it's like an inner ear problem. Actually, the research is not quite settled there, I would say. So where is the biomarker? Let's have a look at some of the results. Just kidding, I can't show the results. So let's pretend this is an awesome figure from my work. We looked at, we have 2 papers in the work. They are really exploratory, right? So this paradigm has not really been used before at the time of collecting the data. Since then, I think a study, maybe 2, have come out that do use this paradigm for measuring tinnitus and the absence of tinnitus within patient. So this is really interesting, right? So we can get a perspective on the patient's brain signal in the like in both cases, right? So both when they have tinnitus and when they don't have tinnitus, which is much nicer than having to give healthy people tinnitus for a tiny bit. We don't do that actually. So yeah, this is a new paradigm, and yeah, I'm very happy to see that you're appreciating the figure. The figures that I actually made for the papers were not made in Mathematica, but they look somewhat similar to this, I would say. Yeah, this is a good representation. So yeah, we looked at we looked at 2 different things at the stimulus onset. So they got 2 different stimuli, one which was going to remove their tinnitus for a bit, and one that was just an arbitrary auditory stimuli that shouldn't affect things. And we looked at the onset here. We found some expected ERPs, right? So it's an auditory signal, and so you're always going to be expecting some ERPs. But we also found 1 or 2 that were unexpected, and maybe this could be a first step towards novel biomarker for tinnitus, at least maybe in some patients. Alternatively, we also looked at like a post-stimulus frequency analysis, and there we were really fitting the temporal pattern with like a segmented linear regression. So this is linear regression, except you segment it at different parts of the time series. So it sounds maybe complicated, like linear splines. Oh, what is that? But it's actually just a linear regression. And we saw that really taking the temporal dimension into account was quite obvious here, because even when they are slightly temporarily experiencing diminished tinnitus or even completely reduced tinnitus, it will start going back again after a time. So we were expecting really a strong temporal pattern here. But the problem is this is exploratory, and within tinnitus patients, we have no idea how healthy people would respond to the same stimuli. Moreover, we know that tinnitus is highly age dependent, also depend on other factors, and so just finding a healthy control is probably not going to be enough. We probably need very closely matching demographics that do not have tinnitus, and then really also perform the same experiment on them, and then see if yes, indeed, these 1 or 2 unexpected ERPs, they do stand out for patients, but they do not stand out for healthy people. Okay, that was the conclusion here. Unfortunately, not enough to really make like a medical device that will measure your tinnitus quite yet, but I would say it's definitely enough to look more into it. But I think that's the conclusion of every paper, right? So like very interesting findings. So we hope to look more soon, to look further soon. Okay, so that's it. Thank you very much. I stole this. I borrowed this template from SlidesGo. So I have to keep this here. But yeah, if you have any questions, then you are too late. Too bad. I'm closing this. No, just kidding. You can ask now. Yeah, further research is warranted. Exactly. That's the sentence. You know it so well. It's practically drilled into you. All right. Thank you so much for paying attention to this. Thank you for your interaction. I think we did well with the audience interaction and the timing. It ended up well. Yeah. So if there's further questions about either the paper, how to avoid these EEG false positives, or if there's questions about maybe a bit more my work, I can tell a bit more in person. That should not be a problem. I know that there's someone here, maybe it's also in chat, but I think someone at the lounge also, or somewhere else at the server, was curious about EEG analysis. Obviously, I'm not the best person to ask, but yeah, that's the paper. Exactly. It's a cornerstone, as you said. That's so accurate. Yeah, very nice. Thank you for linking it. It's in the slides as well, the full reference, so you can find it. Used because that's what has the most documentation in today's scientific research. Yeah, so that's a very good question, and thank you. This really points at something else that I should have explained also. The linear segmentation model was chosen because it is essentially the simplest model that we could use that still takes this temporal domain into consideration, right? So like, let's say a single linear regression has like only like 2 extra degrees of freedom. If you add some knots, like if you add breakpoints after which you fit another one, you're only introducing a single extra degree of freedom. So plus the slope maybe. So this is actually a really nice way to limit your model while still being able to fit like temporal changes. Now, of course, for getting a diagnosis or getting a prediction out, you don't need to limit yourself to the simplest model to get like a statistically rigorous story. No, actually, instead, you might want to use the most sophisticated model, in fact, because you can cross-validate and you can do all these things. And this actually is much closer to my field of study and my expertise. And the long and short of it is, yeah, we tried a lot of different things, including pre-trained neural nets that we then fine-tuned for our data, or that we used for our data as well. We tried finding different features and then used like boosting algorithms, like XGBoost and such. And actually, we did find with very rigorous cross-validation, we actually did find an accuracy beyond guessing, right? So if there's like 2 options and the data set is balanced, and your predicting algorithm is just guessing it's either tinnitus, or let's say it's either the patient is either experiencing tinnitus or they're not experiencing tinnitus, then we are expecting 50-50 if it's just guessing. And actually we found something better than guessing, but it was only at like 60%. So it's working a little bit, but it's nowhere close enough to actually get a practical use out of it. So yeah, we tried a lot of things actually. This is really my primary contribution to the project, I would say. But yeah, we didn't get super far, unfortunately. There's some issues with using the experiment or the data for this specific purpose, because the experimental design is not super nice actually for this specific purpose. So yeah. So what's the math mechanism to reject something that is only as good as guessing? Right. So that's a really good question. And so this is something I'm much more comfortable talking about. The way this is typically done in machine learning is that we train on some data and then we leave some data as completely unseen. And we do this for many different independent subsets, let's say, of the data by slicing it differently again. And we can get an idea of how varied the accuracy is, let's say, of the model when trained on different parts of the data and tested on different parts of the data. Then we can say, okay, so if the model is randomly guessing, of course, we're going to be expecting 50% accuracy on average. But of course, a random model is going to be maybe sometimes 45% accurate, like 55% accurate. And so we can look at how many standard deviations away from this is would be a good model, right? So let's say we want to look 3 standard deviations away at least. And we found that 3 standard deviations was somewhere around like 55%, 58%, I think. So 60, 61% is definitely like in the beyond like 3 standard deviations. It should be significant, but it's like barely, right? We may as well just be unlucky or lucky. Yeah, the paper is amazing. Like I said, I mean, this was super inspiring to me, right? So if we had submitted a paper, we could have told a super convincing story. This is what they're saying. And yeah, I mean, I would not be surprised actually if you go on Google Scholar right now and you can find papers that are presenting results like this. So they don't point any fingers. They just mention that there is like a reproducibility crisis in these types of works. But I feel like I have seen some approaches like the bogus results from before. So yeah, and you don't really always know, right? So the authors, if they're not transparent, you don't really know how much of this has been hypothesized after the results were known or not. So it's really difficult to counter this when it happens. And this is why the incentives are so important, right? So this is why we really need to incentivize good research first and foremost. And quantity is like only a far second. Should be only a far second. Yeah. I'll stay a bit around if there's more remarks. I'm so grateful for all of your input. I'm happy that the original paper got pulled up. I should have linked it in chat. That was such a good idea. Thank you so much. Let me thank you for that. Right, so it's like thanks. Is it?
So I've just sent in some some squiggles. So these are brainstem auditory evoked potentials. These are average. I don't know how many times, but these were the last set that my text gave me a couple months ago.
Okay.
And just the technical challenge of getting something accurate in the first place is really difficult, I think.
Yes. Yes.
If you look at this page, I'm not sure how convinced I am. I'm convinced that the marks are correct. But you see, even the baseline has so much electrical noise, and when you're dealing with something that's this small in amplitude, I have a lot of extra skepticism. the averaging helps, and that's that we do this clinically as well as how you guys do it in research. But as you can see here, it only goes so far.
For sure, yeah. Part of what really helped me convince myself that I didn't have bogus results, even after we do this averaging over all trials and not just one condition, is that the machine learning model was picking up on something, and it was like in the low 60s. So that's also really nice. That it is actually beyond guessing. So it's multiple approaches leading to the same conclusion, let's say. But yeah, in this case, it's hard to say, right? It's always like you say, they're like so small differences, and if you look in the literature, they're reporting on sometimes they're reporting on smaller than 1 microvolt actually. So if you think the example from the paper of 1 microvolt is the difference is crazy, there are much more smaller findings reported, let's say.
But if it's smaller, at some point we kind of wonder, do we, as a clinician, I kind of wonder, can I believe any of that?
Yeah, for one patient, maybe not, right? So
like when we read EKGs, when we read EEGs, sorry, I dropped my microphone. When we do EKGs, right? When we're looking at the heart, when we're looking at peripheral nerves, all those things are microvolts typically. Mostly they're microvolts. So you have these large, robust signals, but then once you get into the brain, it just becomes 3 times as challenging. And just the old saying that if the signal's poor, the result is also going to be poor.
Yeah.
So I'm not saying anything you don't already know, though.
No, it's just that you're drawing like a super important distinction here, is that what is statistically significant, and let's say they are real true positives and they really have to do with the task at hand and they lead to real insights about the brain. Even then, it's not obvious how this should be applied in clinical practice, right? Because in one patient, there's no way it's going to be like accurate or sensitive enough to spot this, right?
Right. The other thing is, a lot of the things that we do, right, is we're car mechanics, right? If when we're measuring visual potentials, we know they're at the back of the brain because we know it's occipital cortex. We know that's where you should get a VEP, and it's been validated over 50, 60 years.
Yes.
Whereas here, this is all kind of like, what is it? The Wild West.
Yeah, in a sense, it is. It's in
Like-
one sense, it's really talking about uncharted, like charting uncharted territory, right? So we need to have.
Yeah. What is at FP1? I mean, I'm not sure I should see anything at FP1, right? It's, maybe it's frontal, maybe it's frontal cortex, maybe, but
maybe it's deeper. Yeah.
So that's challenging. And then there's the fundamental EEG thing is the what is it called? The there's a name for the problem, right? The theory, the basic idea that any potential field can have an infinite number of representations or something like that.
Yeah, I remember what you're talking about. Yeah.
So, okay. That's
no, it's
but very interesting.
Thank you so much. Thank you also for your input. I think you're drawing a very important distinction for what steps are necessary before we can get anywhere near to the amount of rigor and reproducibility necessary to make this even useful, even if we do find something significant. But yeah, I mean, this is kind of how it is, right? We have nothing at the moment, and we're just grasping at straws in a sense. Having objective diagnostics would quantifiable diagnostics for tinnitus would help so much.
Yeah,
because
it's exciting too. But there's one more thing. I'm so sorry to interrupt.
That's okay. I'll continue.
Before I forget, it's tinnitus is subjective, right? You feel it.
Yes.
And two people may feel two different things. In clinical neurology, we also have something called pulsatile tinnitus, which is not tinnitus. It's people hearing whooshing because they're hearing the transmitted sensations when you have increased pressure in the brain. So like somebody has a big brain tumor, they'll hear whooshing in their brain. But that's not tinnitus. Tinnitus should be a high-pitched
it's really a phantom sound, but it doesn't have to be a single pitch. It can be oscillatory, it can be noise.
Yeah. But you can feel it. But how does somebody else, how does the clinician measure it in the first place?
Very good.
So that's our challenge. That's our challenge. Someone comes to the clinic and says, I feel this. I'm like, okay, well, I believe you. What am I supposed to do about it? How do I know it's real?
Yeah. So I was working with M&E a lot. It's like a library for processing this. And the maintainer of that library did some research as a treatment, which is very interesting. So normally one treatment is just cognitive behavioral therapy, and that's not because it doesn't solve the tinnitus, but it really solves the distress related to the tinnitus, or it can help with the distress related to tinnitus.
For sure. I feel like that's all of psychiatry. It's
Yeah.
You have a condition, we know it's real, right? Depression is real, anxiety is real.
Yeah,
There's no question
yeah.
about it. But we don't know the mechanism. We don't know what's happening in the brain. And this is
Yeah.
true for actually a good chunk of neurology as well, right? We
Yeah.
know what it looks like because we've seen it for 200 years. We know what works because we've done it for 200 years. But it's very unsatisfying. You know, like it's somebody who wants, like, you want to be a mechanic, you want to know the mechanism, you want to be able to replace the part that's broken, and we can't do any of that.
Yeah, and so they actually compared to getting direct neurofeedback from either EEG or fMRI. They basically showed just what the activation was at like a specific location in the auditory cortex, and they were then tasked to lower this activation. That's all that they were tasked with, the patients, and they found a significant improvement in the and they found that just giving the patients direct access to their cortical activation really allowed them to just through introspection modulate their own response to the tinnitus. And it was actually the fMRI based one was actually statistically quite a bit better than just the CBT. And I imagine they work together as well. I don't think they have to be completely separate. So that was super cool work. And yeah, I met with this person and talked a bit with him, which was super nice to do. But yeah, this entire field is fascinating and really difficult because of what you said, how complex and how much noise is in the signal. But it's important still. If, like what I was saying before, if we have quantifiable diagnostics, then we can do much more accurate testing in how well our treatments work. Because now the patient may be reporting no reduction because they're feeling particularly distressed that day, even though the actual volume of the underlying process that generates the tinnitus has been lowered, right? So it's very subjective, but maybe actually there has been some progress that the patient is not aware of. But we can't see this at the moment because we only have subjective measures. Yeah, and I mean this is true for all of the exploratory research, really. So yeah, I'm very conflicted on this side of the aisle, of the research aisle, because as you said, it really is Wild West, and you see that, you feel that when you're doing literature review. To start with, you can be very cautious sometimes to include the paper if it doesn't really meet your standards, because as you said, I mean, does it really do everything correctly? Is it really transparent or not? Or is it maybe just a false positive? Maybe they're reporting something just to have something to report. And you feel that on when you're doing the literature review, and you feel the steep cliffs on either side of the rigorous path, let's say, when you're doing the research yourself. And I think it's just good to be transparent, right? So in our research, we just also say, like, this is super exploratory. It's also like very likely that these are just very spurious as a result from this analysis and not from anything, and we really need further testing. But this is a first step. Someone has to take a step, I think. And that was what I was doing. But it's some months ago now since the contract ended there, so it's in the past for me. It's out of my hands.